Okay. So welcome back, everyone. I hope you all had a relaxing spring break. I wanted to spend a couple minutes today. I know probably, right, we've been gone for a week, which means we've forgotten 73% of what we've learned so far about convection. So we're going to spend a couple minutes doing some review of like the week leading up to spring break before dipping our toes into the problem of scaling. Okay. A couple other sort of announcements of what's going to go on between now and the end of the semester. Probably sometime next week, I'm going to hand out the semester design project. Right, this is an important part of the course. It's going to consist of, in broad strokes, designing a heat exchanger or a heat sink using the convection correlations we're going to be talking about in the next couple of days, and your one-dimensional extended surfaces or fin equations from the conduction chapter, right? So I'll give you some sort of piece of equipment, a motor, piece of electronics, etc., give you some dimensional sort of constraints, and it'll be up to you to come up with a reasoned choice of design, right? Number of fins, type of fins, size of the fins, the type of substrate you're using, and you're going to have to combine some of the concepts that we've been talking about so far. You'll have a couple of weeks to work on that, but expect to turn in, a short little design summary and a set of calculations. We'll talk about that more in detail. Before we get into that, we're going to try to get through the basics of convection so that you have everything you need to know before I hand out the project, right? So, lecture 22. Like I said, quick recap. Right, convection we have established is, right, the heat transfer between an object and a moving fluid. And by its name, we know it's a combination of two different actual mechanisms, which are, the first, right, where we get the con, is conduction, and the second is advection. So we have the convection, can be thought of it as a conduction, which is the heat transfer in the slow or non-moving fluid near the object, plus advection, which is the bulk motion heat transfer in the faster moving flow. Right. So the way we describe convection, right, our heat rate comes from which of our three heat rate equations? We've got Fourier, we've got Newton, and we have Stefan Boltzmann. So remember Newton, right? Newton's law of cooling. So the heat rate comes from Newton's law of cooling, where we say that Q double prime, normal to a surface, is equal to H times the temperature difference between that surface and surrounding fluid. So heat flux, if we were to integrate that heat flux over the area of whatever surface we're considering, H Ts minus T infinity dA, right? We would get the heat rate. And an alternative way of getting the heat rate is if we were to sort of move all the constants, if we were to move, for example, this temperature jump outside of the integral, we would end up being able to write the same Qn as h bar times A Ts minus T infinity. So this is also the heat rate, but using an average H. So flux, right, in watts per meter squared. This is just in watts, and this is just in watts. So these are the quantities we're usually interested in because this tells us how much heat, how much thermal energy is going from one place to another, right, in a language that we understand and a language we can give people, right? We can dissipate X number of watts. Then we have some constraint to give to, the designer of an electronic system, for example. So the question, right, and what our task sort of boils down to in this chapter is figuring out H, and in some cases H bar, where H bar is equal to 1 over A integral surface area of H dA. So that itself also boils down to finding H. So our goal is pretty single-minded in this chapter. What is the convection heat transfer coefficient, H? So we call this like our driving question. What is H? Or rather, how to find H. Okay. So we went ahead and we set up an energy balance, right? We say if we have a fluid flowing past an object, then we're going to have, right, this development of different kinds of boundary layers. There's a thermal boundary layer, a velocity boundary layer, and the only task of a boundary layer, or the role it plays here, is that it's a region of transition between the value at that surface and the value in the fluid. Okay? So thermal boundary layer, you have this curvature that describes the temperature variation between the surface temperature and the fluid temperature in the free stream. Same thing for the velocity. And if we're dealing with this problem of species transport, where you have concentrations of matter, okay, then you'll have a concentration boundary layer as well. But the thing was, we said right at that boundary between, right at that infinitesimally small layer of fluid that's sort of stuck to our surface, right, we can set up an energy balance and saying that in that layer we have only conduction, right, because there's no velocity, zero slip boundary condition. And so all the heat that leaves through this convection, right, into the fluid has to pass through this tiny little region by conduction first. And using that approach, we came up with this equation that we're going to keep coming back to. H equals the conductivity of the fluid times the rate of change of the temperature at y equals 0 divided by Ts minus T infinity. And so what we're talking about here is, right, if we have some surface at a temperature Ts, the fluid is at some temperature T infinity, and we define y as being positive up measured away from the surface. Okay, so we've basically just got our Fourier's law here, and then if we were to bring this up here, we would have Newton's law of cooling. So it's setting those two things equal to each other. But, right, the issue with this is we want to find H. Okay? If we want to figure out how to come up with these Q terms, if we want to find H, we've got to know our T distribution. Okay. So, right, this requires T of y to be known. If we want T of y, we have to solve this so-called energy equation, which we will write up here in a second. But remember, this is one of those long, nasty governing equations. To solve the energy equation, okay, we need to know, right, boundary conditions. That's usually fairly easy. What other piece of information do we need to know to solve this energy equation that we don't usually just have up front? Anyone else remember? Right? The temperature distribution or the energy equation depends on the solution to one other equation. Right? It's because we need to know the velocity distribution close to the wall, right, in order to get T. If we're solving a problem that involves convection, right, the flowing of fluid, we need to know how that fluid is flowing before we can figure out how the temperature distributes itself. So this requires that we know the velocity u. Right, so we have to resolve that velocity boundary layer before we can find the temperature distribution. Right? So to solve u requires that we solve the Navier-Stokes equations. Right? And so solving the Navier-Stokes equations gives us u. And so this process just becomes really laborious. Right? We have to be able to solve this. Then we take that and we plug it into the energy equation. Then we solve the energy equation, and it becomes a series of multiple steps of solving these partial differential equations, plugging in boundary conditions, and then finally we say, all right, I know T. We take the derivative of T, plug it in here, and I finally have H. It's not impossible. Well, I should say this process is almost always impossible because most realistic problems, most geometries, engineering systems, we can't solve them. We can't handle the math to get this or this, let alone both of them. There are a few simple cases where we can. So to demonstrate this, we're going to go ahead and walk through one more of these classic problems where we can actually go through this, wind our way through this sort of snake of problem solving. And then we're going to talk about some easier ways to tackle it, right? Using scaling, dimensional analysis, and experimental correlation. So previously, right, we did a similar problem to this one. So consider two. Well, here, actually, let's make this vertical. Let's consider. Consider a vertical, sort of the vertical space between two infinitely long plates. Okay. So both of these plates are fixed plates that extend. It's an S that extend infinitely long into the page. Go ahead and set up our system of equations as x and y, and we'll say that we have some fluid between these plates that has the following properties. Okay, this is a fluid with a density equal to 1 kilogram per meter cubed. Oh no, we'll say 10. Make that 10 kilograms per meter cubed, and a viscosity, mu, equal to 1 times 10 to the negative third Newton second per meter squared. Okay. This thing's oriented vertically, so we're going to go ahead and say that, yes, gravity is pulling on it. And then we're going to say that this wall here, right, the temperature of this surface is at 300 Kelvin. And the temperature at this surface is at, going to be at 350 Kelvin. Okay. So already what we're setting up here, imagine what this could be. There's a type of heat exchanger, right? The type something like they use these in a lot of industrial processing settings. They use them on ships and in water treatment centers. These things called plate type heat exchangers, where essentially you'll have a bunch of parallel plates stacked together vertically, and you'll set some hot fluid flowing past one, on one side and a cold fluid flowing past another. Okay, and the idea is, as the name would imply, you want to get some of the heat from this hot fluid to this cold one. But if you were to look at just one side of that, it would look kind of like this, right? You might have this cold fluid here has a hotter temperature over here than over here, and it's being pulled down under the influence of gravity. That's how it would be flowing. Okay. So the question is, how would we find the effective heat transfer coefficient that tells us the heat transfer from this point to this point? Okay. Let me see what other properties we need to give. This whole thing has a width of h equals 10 centimeters. And one moment, I need to calculate something on the fly. Calculator. I'm going to tweak this density a little bit. 10.2 kilograms per meter cubed. The reason for this is going to be pretty simple in a second, or pretty clear in a second. And finally, okay, and then this fluid also has a fluid conductivity, K sub F, of 0.6 newtons per, watts per meter Kelvin. That should be everything. Okay, so our assumptions that we're going to use to simplify our problem solving include the usual steady state, right? Two-dimensional, or really one-dimensional, where this means that u is equal to 0. And so we end up with v is equal to a function of x only, and t is equal to a function of x only. And we'll assume that we have pressure is uniform on y. That is, that the pressure is not varying from top to bottom. Okay. So we've got these three kind of governing equations, right? Or equations that govern three behaviors. First is conservation of mass. Second is conservation of momentum. Third is conservation of energy. All right. Conservation of mass, once again, usually the easiest one to start out with. Conservation of mass. We're going to zip through these first two, and then I'm going to hand over the conservation of energy for you guys to chew on for a couple of minutes. Then we'll come back and discuss. Conservation of mass, we have du dx plus dv dy is equal to 0. Right, of course, we here we say u is equal to 0, which means everything that all derivatives of u go to 0. And we say then that tells us dv dy is equal to 0, which tells us this is a fully developed flow. And that essentially confirms what we have right here, right? That we're saying that this is not varying as a function of y. Okay. Conservation of linear momentum. Oops. Or the better known as the Navier-Stokes equations. We're going to look at just the y direction. And here we're going to have rho dv dt plus u dv dx plus v dv dy is equal to negative dp dy minus rho gy plus mu d squared v dx squared plus d squared v dy squared. So, right, once again, in this case, we would go through and cancel out. We'd say u is equal to 0. That's 0. We know that v does not vary as a function of y, so that goes to 0. We have our steady state. We've said that the pressure is uniform on the y direction, which means this derivative goes to 0. V does not function, or is not a function of y, so that goes to 0. And rho times gy is going to, essentially, this is going to boil down to a quantity of 10.2 kilograms per meter squared times 9.81 meters per second squared is going to give us a quantity equal to 100 pascals per meter, right? Or negative 100 pascals per meter, which we can plug in later. But right, we've canceled everything out except for a known quantity here and our second derivative here. So setting it up, solving twice, or integrating twice, we would end up with a general solution that looks like following. 1/2 mu rho gy y squared plus c1 y plus c2. Okay, or that should be an x. All right, so general solution, once again, we plug in our known boundary conditions, find C1 and C2. Anyone know what those boundary conditions are? Looking at this, based on what we've got. Boundary conditions on the velocity. What 2 points here might we know the velocity? I heard 0 at one wall, both walls? Both walls. Okay. So we've got 0 here, and we've got 0 here. It gives us our two conditions at two different places. That should fully define the problem. So if we applied those boundary conditions, I'll spare you the details here. We'd end up with Vx is equal to negative rho gy over 2 mu y times, x times x minus h. So what this is going to look like is as follows. Well, let's go ahead and say this is x, here's 0, here's h. Our velocity distribution is going to be this parabolic sort of behavior, where it's going to be a maximum at the very center of the pipe. So if it's just flowing down under its own weight, this is what we're going to end up with. And we should get, if we were to plug the numbers in, we should find that this has a maximum of somewhere around, this is approximate, I'm just looking at the graph I plotted out before, about 125 meters per second, actually. Quite a rapid clip that it's moving along at. Okay, so if this is V, right, we we have our solution. So now we would move on to, right, the energy equation, which uses this information to give us the temperature distribution across the same gap. And that temperature distribution is going to allow us to learn more about the convective heat transfer coefficient. So our energy equation is going to take the following form: rho c dt dt plus u dt dx plus v dt dy equal to k d squared t dx squared plus d squared t dy squared. There's our diffusion term, plus q dot plus mu times 2 du dx squared plus 2 dv dy squared plus dv dx plus du dy squared. And yep, that's it. Okay, so from here, right, we should be able to cancel out everything except some derivative of t and maybe something about the velocity distribution. All right, so that, I want you to spend the next couple of minutes, like I said, sort of gnawing away at this equation and see how simple you can get it based on the assumptions that we've been given and the kind of the problem geometry as well as the solution for the velocity. Alright, where you should be sitting at the end of this is something that looks like the following. I'm going to give you what you're looking for. 0 equals k d squared t d x squared plus mu dv dx squared. Does anybody get this out of here yet? we've got a few more minutes to. All right, and show of hands, how many now have managed to cancel enough terms that they've got something looking like this? All right, most of you. Well, we're going to go ahead and, since most of you have gotten here, let's go ahead and just quickly step through for those of us that might have a couple of terms that we can't seem to shake off. This first term right here, right? We get rid of that because of which of our assumptions? Steady state. This term right here, because u is equal to 0, right? This term here, right? That we have, that t is a function only of x. This term here, right? We've kept, because we simply don't have any excuse to get rid of it, right? That's one of the reasons it finds its way down here. But what about this term here? T is a function of x. This q dot, I suppose I didn't say anything explicitly about the q dot. As a rule of thumb, in my class and probably in ensuing classes as well as in industry, you'll be told ahead of time, hopefully, whether you're working with some sort of radioactive material or something that's going to try to generate heat and blow up. So unless you're told that, certainly in my class, you get to assume that q dot is equal to 0. Okay? I'll make sure to tell you if there's electrochemical heating or some sort of nuclear heating of the fluid going on. That goes to 0. This term here, I heard it somewhere, u is equal to 0. This term here, right, v is a function of x. This guy here we chose to keep, and then this guy here, it's again, u is equal to 0, right? So the only terms that we've managed to retain are this guy and this guy, which find themselves down in our simplified equation. Right? So this is something that we should be able to solve pretty much directly, okay? Because we've got v from our previous solution, and so if we figure out, our equation for dv dx and plug that in, then we should be in good shape. So in this case, if we went ahead and said dv dx is going to be equal to negative 1 over mu rho g y minus h over 2, and we plug that into this expression here, we should be able to isolate our d squared t d x squared is going to be equal to negative mu over k, or equal to positive mu over k 1 over mu rho g y minus, or So this should be an x. Sorry, I solved this thing in a 90-degree rotated coordinate system when I did the example. So I'm doing these conversions from a horizontal system to a vertical one on the fly. So please holler at me if you notice that I've plugged in a y. There's somewhere there should be an x. Squared. Okay, so here's our governing equation, and we've gone ahead and substituted in our solution to the Navier-Stokes equations to arrive at something, an ordinary differential equation that we can actually solve directly. So if we integrate once, so this becomes a messy problem. It's not necessarily difficult. It's just kind of it turns into a lot of bookkeeping, because once you square this, right, you're going to end up with something. This should actually be an h over 2. So once you square that, this is going to look like the following: d squared t dx squared is equal to mu over k . 1 over mu rho gy squared times the following: h squared over 4 minus yh plus y squared. Okay. So go ahead and take a couple of, Huh? No, I haven't integrated yet. I have just expanded out that squared term, right? Huh? Oh, yep. If it would let me erase, I'd fix that. There we go. X and X. Does that look right? Yes. Okay, there we go. All right, so go ahead and take a minute and see if you can integrate this twice to find t. Hands up if you found something that looks like this.
C1x.
Yep, C1x. There we go. All right. So, integration once. Give us our first constant of integration. Twice, give us a second, which means we've got our general solution. We have to plug in boundary conditions. Looking back at the problem definition, I'm going to scroll up here for a second. There we go. Our boundary conditions here, right, for temperature should be even more apparent than those that we used for velocity. Right? Given a temperature at one wall, 300 Kelvin. Given a temperature at another wall, 350 Kelvin. So we would plug those two things in right at the two different values of x. Right. Boundary condition number 1 would be temperature at 0 is equal to, we'll go ahead and call this T cool, or TC. If we went ahead and plugged in a x equals 0 everywhere in here, the only thing we'd end up with is our C2, right? Fantastic. Just a second. There we go. The only thing we'd end up retaining is that C2 constant of integration. So this would tell us then that C2 is equal to TC, or 300 Kelvin. Right, that's the easier of the two. Boundary condition number 2 is a little bit more involved, because this tells us then that T of x at x equals h is going to equal T hot, or 350 Kelvin. Okay, so plugging in an h for everything up there is going to get us an equation that looks like following. Mu over k yep, 1 over mu rho gy squared times h to the 4th over 8 minus h to the 4th over 6 plus h to the 4th over 12 plus, right, C1 h plus C2 we solved before, so equal to T sub C, and this should all equal T hot, right? These guys luckily boil down to something a lot simpler. We can write this instead as simply h to the 4th over 24. We collect those fractions, and so what we should get if we were to solve for C1 this is just algebraic. C1 is equal to T hot minus T cold over H, right? So there's sort of a linear variation component. Minus mu over K, 1 over mu rho G y squared cubed over 24. Yes. So we've got C1, we've got C2, plug those in, and we're going to end up with T as a function of x be equal to over K, 1 over mu rho gy. There's our h squared, x squared over 8 minus x cubed h over 6 plus x to the 4th over 12 plus T1 minus, or sorry, TH minus TC over H plus mu over K 1 over mu rho g y, and this should be a minus sign actually, squared h cubed over 24 times x plus t cold. All right, so there's our particular solution. And what this is going to look like then is actually set x and temperature. We've got our Tc, which is equal to 300 Kelvin, and we have our Th equal to 350 Kelvin. This is going to take on a character that looks sort of like this. It's going to have this sort of wobbly behavior with a general increasing trend. And you remember these reasons we get these sort of nonlinearities, right? They come from all of these terms that have, right, these, yeah.
Is it 1 over mu rho times g squared?
Rho times g squared, yes. That first term right there. Yeah? And the reason we get these nonlinearities, right, is they're all tied to these cases, these parts that have mu in them, right, viscosity. So these come from the tendency of the fluid to, right, to generate frictional heat due to viscous dissipation, right? So we're bumping up against time here, but now if we wanted to find our convective heat transfer coefficient between our left plate and our right plate, if we wanted to find H, and we'll outline the steps here. To find H at this point, we'd come back to this expression for H. H equals K dt dy at y equals 0 at T s minus T infinity. This is how we wrote it before. Right? In this case, we would change it a little bit because we're sort of, we're not solving t as a function of y, we're solving t as a function of x. So we would kind of tweak this equation so it is kf dt dx at x equals 0. And, right, rather than the surface and fluid temperatures, we would be saying, right, the temperature at the surface would be like T hot, for example, and then the fluid temperature, or the temperature far away from that wall, is actually going to be the cold wall temperature. So we would take this equation and differentiate it once to find the slope, evaluate that at x equals 0, plug it in there. K sub f, right? So we'd use this solution, plug it in there. K sub f comes from the problem definition where we said that Kf was equal to 0.6 watts per meter Kelvin. Okay, that was just a given property of the fluid. We plug that in there. Th and Tc, or sort of our temperature limits, okay, would be given by the problem definition where we have 350 and 300 Kelvin respectively. 350 Kelvin and 300 Kelvin. So it just becomes a matter of crunching those numbers. But right, this is a laborious process, and because we don't have time, we're not going to go ahead and do this. So what we're going to work on next time is an easier way of attacking this problem known as scaling. All right. So I'll see you guys all on